A brown dwarf is a type of astronomical object that exists between the largest planets and the smallest stars. These substellar objects are often referred to as failed stars because they are not massive enough to sustain nuclear fusion of hydrogen, which is the primary energy source for stars. However, they are more massive than most planets, and they can undergo limited nuclear reactions early in their evolution. Here's everything known about brown dwarfs. Brown dwarfs have a mass between approximately 13 and 80 times that of Jupiter, or 0.012 to 0.08 solar masses. Objects below this mass range are typically classified as planets, while those above are considered stars. Brown dwarfs have a mass between approximately 13 and 80 times that of Jupiter, or 0.012 to 0.08 solar masses. Objects below this mass range are typically classified as planets, while those above are considered stars. Brown dwarfs occupy the range between the least massive stars, such as red dwarfs, and gas giant planets like Jupiter. They do not undergo the main sequence phase of stellar evolution because they lack sufficient mass for long-term hydrogen fusion. Although brown dwarfs cannot fuse hydrogen, objects above about 13 times the mass of Jupiter can briefly fuse deuterium, a heavy isotope of hydrogen, in their cores. Deuterium fusion occurs at a much lower temperature than regular hydrogen fusion and lasts for only a short period in the brown dwarf's early life. Brown dwarfs can also fuse lithium if their mass is above about 65 Jupiter masses. The presence of lithium in an object's atmosphere is used as one method to distinguish brown dwarfs from stars, as stars quickly deplete their lithium. Brown dwarfs are similar in size to Jupiter, even though they can be up to 80 times more massive. This is because their higher mass compresses the material inside them, leading to very little increase in radius. In fact, as brown dwarfs become more massive, their radius actually decreases slightly due to this compression. Brown dwarfs are denser than gas giant planets, but less dense than stars like red dwarfs. Their density increases with mass due to gravitational compression. Brown dwarfs have atmospheres composed mostly of hydrogen and helium, similar to stars. However, their cooler temperatures allow for the formation of molecules like water, methane, and ammonia in their atmospheres. At the highest end of their temperature range, some brown dwarfs may have clouds of silicate or iron particles. Brown dwarfs are much cooler than stars. Their surface temperatures typically range from about 250 K, minus 23 degrees Celsius, to 2,500 K, depending on their age and mass. Younger brown dwarfs are hotter, but they cool over time as they radiate their internal heat. Brown dwarfs are classified based on their temperature and spectral characteristics into different spectral types. L-type brown dwarfs. These are relatively warm brown dwarfs, with temperatures between about 1,300 and 2,500 K. Their atmospheres often contain clouds of iron and silicate dust, which give them red and brown hues. Molecules like titanium oxide, TiO, and vanadium oxide, VO, are also present in their spectra. T-type brown dwarfs. Cooler than L-type, T-type brown dwarfs have temperatures ranging from 600 to 1,300 K. Their atmospheres are dominated by methane, CH4, and water vapor, and they tend to have a more neutral or blue color due to the lack of dust clouds in their atmospheres. Y-type brown dwarfs. The coolest known brown dwarfs, with temperatures below 600 K, fall into the Y-type spectral class. These objects have atmospheres with even more complex molecules, such as ammonia, NH3, and their temperatures can approach those of gas giant planets like Jupiter. Brown dwarfs are difficult to detect because they are faint and emit most of their radiation in the infrared spectrum. They do not shine as brightly as stars because they lack the sustained fusion reactions that power stars. Several methods have been used to detect and study brown dwarfs. Since brown dwarfs emit much of their energy as infrared radiation, telescopes that can observe in the infrared part of the spectrum, like the Spitzer Space Telescope and WISE, Wide-Field Infrared Survey Explorer, are crucial in detecting them. Some brown dwarfs have been found through surveys that look for objects with large proper motions, meaning they move rapidly across the sky relative to more distant stars. These objects tend to be relatively nearby. Brown dwarfs are often found in binary star systems, where they orbit a more massive star. By observing the orbital motion of the star, astronomers can infer the presence and mass of a brown dwarf companion. In some cases, brown dwarfs have been directly imaged, particularly those that are relatively young and still radiating significant heat from their formation. Brown dwarfs are often found as companions to stars in binary or multiple star systems. In some cases, they orbit relatively close to their host star, while in other cases, they may have wide orbits. Observationally, there appears to be a relative lack of brown dwarfs in close orbits around stars. This phenomenon is known as the brown dwarf desert, and its cause is still not fully understood, though it may be related to the formation processes of stars and planets. One of the key challenges in the study of brown dwarfs is distinguishing them from large gas giant planets, especially as both can have similar sizes and compositions. Several factors help distinguish them. Brown dwarfs are generally more massive than planets. The deuterium fusion threshold at around 13 Jupiter masses is often used as a dividing line between planets and brown dwarfs. Objects more massive than this can fuse deuterium and are considered brown dwarfs, while objects below this mass are typically considered planets. Brown dwarfs are thought to form like stars through the gravitational collapse of a gas cloud, whereas planets form within protoplanetary disks around stars. This distinction in formation mechanisms helps separate the two types of objects. The atmospheres of brown dwarfs can have different chemical compositions compared to planets. For example, the presence of methane in the atmosphere of a cooler brown dwarf can make it resemble a gas giant planet, but the presence of other molecules, like ammonia, distinguishes it from planets. Brown dwarfs are born relatively hot, with temperatures of a few thousand Kelvin. However, they do not sustain fusion, so they cool and fade over time. Young brown dwarfs can be relatively bright in the infrared, but as they age, they become fainter and cooler, eventually resembling gas giant planets. Since brown dwarfs do not burn hydrogen and thus do not undergo a main sequence phase like stars, they do not die in the same way as stars by becoming white dwarfs, neutron stars, or black holes. Instead, they simply cool and dim over billions of years, eventually becoming cold, dark objects. Discovered in 1995, Tide 1 was one of the first confirmed brown dwarfs. It is located in the Pleiades star cluster and helped confirm the existence of brown dwarfs as a distinct class of objects. Gliese 229b. This is one of the most well-known brown dwarfs and was the first to be observed directly. It orbits the nearby red dwarf star Gliese 229 in the constellation Lepus, about 19 light-years from Earth. WISE 0855-0714. One of the coldest brown dwarfs ever discovered, with an estimated temperature of around 250 K, minus 23 degrees Celsius. It is located about 7 light-years from Earth and has characteristics similar to a gas giant planet. Some brown dwarfs are known to host planetary systems, much like stars. These planets are likely to be gas giants or icy bodies, as brown dwarfs lack the energy output to host habitable, Earth-like planets. Brown dwarfs are unique objects that bridge the gap between planets and stars. Although they form like stars, they lack the mass needed to sustain hydrogen fusion and thus remain dim and cool, particularly in the infrared spectrum. Their study has helped astronomers better understand star formation, substellar objects, and the complex processes governing the evolution of the universe. Despite being challenging to observe, advances in infrared astronomy have revealed many brown dwarfs, and they continue to be a fascinating area of astrophysical research.